Okay, so this is our design elements for our CubeSat. We are the GSSM Eagles team. Our members are Steven Signeras, me, Ava Perkins, Ivan Shen, John Jones, and Om Patel. So for our SMART goals that we've decided on, SMART standing for specific, measurable, attainable, relevant, and time-based goals, we want our CubeSat to operate in a 510 kilometer orbit at a 35-degree inclination based on the CY-GNSS. Our CubeSat will transmit data and pictures to the ground station at GSSM, and it will delete the transmitted pictures from its SD card after the GS has confirmed the reception. And we plan for this to take a relatively short time, around 10 minutes for transmission to ground station.
Great. So this here is our concept of operations diagram. And given that most persons we have with us folks like the CubeSat's operations in orbit, we figure we should focus our diagram on what happens while satellites in orbit. So firstly, once satellite has separated from the launcher, its systems will kind of transform like a safe mode to it'll boot up, and each system and a computer will kind of go through each system and perform like a self-check on it. If a computer doesn't find any errors in the system, then we can proceed to nominal orbital operations. But if there's some error, an error is detected and it's confirmed by that computer, the Raspberry Pi reflector will go to communicate the error to ground station back at GSSM. From there, using our knowledge of the codes, we can we'll do our best to troubleshoot and then find a way to be able to circumvent that error. Say if there's like a mechanism or part that is either made short-circuited or otherwise it's not functioning. If we can find a way to either get the part back up running or just kind of work around the part not working, either case, mission will be successful as usual, or as kept release, or the mission requirements might be changed to fit the mission. But either way, it will still be partial success. But either way, if the error is fixed that way, it's still at least a partial success. But if it isn't, then the mission fails, and that's bad, since we want our CubeSat to ultimately detect these particles of these microplastics in the ocean, and can't do that if it doesn't work in orbit. So during the first phase, these systems that will be active will be the power systems, communications, flight computer, all part of these central controls. And if that time is needed, we operate the ADCS, and that will kind of keep the CubeSat kind of oriented correctly. But once everything's good startup, we'll proceed to, I guess, what happens during normal flight. So during most operations, we plan to have like a sort of, one satellite is raised to ground station, we plan to have like a routine status checks to be transmitted from the ground station to the CubeSat, and then the CubeSat will kind of verify. It'll send the telemetry back to the ground station, and this happens every few seconds to kind of verify that that connection is stable. When occasionally we might need to adjust the orbit of the CubeSat so that it remains in that 510 kilometer altitude at 300-degree inclination, which, by the way, was based off a real constellation distinguished program, which is used by the University of Michigan to actually detect microplastic in the ocean. But from that, if need to, the orbit can be modified. And then during the time period, our science mission of taking pictures of the ocean and running, I think, remote sensing to detect microplastics will be connected then too. Now, as for hardware itself, cool. So as for hardware itself, this is like our block diagram. Actually, here. Okay, this is our block diagram of what the system looks like. So this is similar to like diagrams that we guys showed us on the like laboratories website, but each component has each subsystem is contained within the overall CubeSat structure. The flight computer system consists of the Raspberry Pi, as well as like the SD card reader and the SD card itself for like to store our software and all that. Communications in this state consists of the Raspberry Pi Bluetooth capabilities, which will kind of go from our computer-based connotation to the Pi itself, and these will be powered by Raspberry Pi power supply and also our solar panels on the CubeSat body itself. And we also have our attitude determination and control system. Its IMU will be a part of the system too. So as left in their states, you see the orange arrows signify the power connections between the power supplies and each subsystem, and then the data connection, and the blue white arrows symbolize the data connection between the flight computer and each system, except power, but data is being sent to and from the camera, the ADCS, the IMU, and the communications array to the computer, and that is being transmitted. That would be intended to mostly we transmit back, and we'll come back to the current system as well. And then now to talk about applications is Ivan Chen. So
for our communication system, we chose to use Bluetooth with OBEXFTP. So we have it so that our system uploads the pictures taken by the CubeSat to the ground station, and upon successful transmission, it deletes the sent photos to conserve storage. To send the photos, we have the CubeSat periodically checking for a Bluetooth connection with the ground station, and once it finds this Bluetooth connection, it sends and uploads the video, the photos. In the event of an error, we plan to have the CubeSat save the non-transmitted photos and send them during the next transmission. And then down in the last line, that is the code that we are currently using to send the photos.
And now talking about power is John Jones, who he actually recorded this part asynchronously. So with a good splice, his part should go right here.
Okay, hello. I am John Jones, and I will be presenting the power system. So the power system is pretty simple concept. So starting over here, this is the EPS. It stands for electrical power system, and so it's made up of the power source. This is the satellite, energy storage, which is the battery, and then power distribution, which distributes the power throughout the system, and then the power regulation and control, which controls the power in the system. So you get your power. Well, the power source really is the solar panels, and so to get the amount of voltage or amps, you would arrange solar panels in something called a series or parallel. So in a series, to get more voltage or increase the voltage and the power, you would use the structure of series. So it's whether you have the solar panels on top of each other. And so right here, you see we go from 12 to 24 volts. And to get more amps, you would arrange solar panels in parallel, side by side. So right here, we see we go from 5 to 15. Over here, this is how the power kind of works or like travels. And so when you have, I guess, full sun or full whatever, how much power fully, the power is distributed through the loads, just through the loads and the battery charger, which charges the battery, and then the excess power goes to the shunt regulator and out here to the radiator. The CubeSat won't have this part, obviously it's too small and it isn't really needed. And so during an eclipse or whatever, we don't have that much power coming from the sun. the load will get its power from battery. And so that's why during like the full sun, when most of the power is shown throughout the day, the battery charger charges the battery, so the load will be able to get its power from the battery. And so yeah, that's pretty much it. So yeah, this is the power system.
Okay, so the camera is a part of the CubeSat that's main responsibility is to take pictures and identify objects, and it's practically the eyes of the system. The camera connects directly with the Raspberry Pi as seen in the picture, and it can contain many different methods such as brightness, annotation, and contrast, and a lot of others to adjust the picture the way you want it. And for the code, here's a sample code where we just initiate the camera, start it, have it sleep, take a picture, and then stop. What we did was we had the code make it so the satellite takes a picture as soon as the satellite itself faces a vibration greater than 10 on any different axis. And that allowed it to just know it instantly when to do it. And next is the CAD. For the CAD, we used Tinkercad to create a model, and we used all the parts given to us from Revolut. So as you can see, the whole process of CAD is used to design a model and find future problems that we could find or that we have to solve. And as we found for our design is that we had a bunch of holes that we needed to drill into our design where there wasn't any in the first place. So we had to go fix everything with that. And we built it all in Tinkercad. We modeled everything, and that allowed us to find step by step the correct way to help build our CubeSat to how we have it currently.
So for the other picture, that is our current structure for the CubeSat. So we use the model in Tinkercad to roughly build the exact same satellite. It still needs a few modifications, such as the holes drilled, but otherwise it should be perfectly fine.
Thanks, Evan. I believe. Yep. So folks at BWSI, thank you for having the GSSM Eagles team in this competition.